in the paper that I'm going to present, we really do two things. We give a new algorithm for Oblivious type compaction, and we also give a careful accounting of that algorithm in terms of its runtime, the linear term and the asymptotic, the leading term, and also we show that the failure probability of our algorithm is negligible in n. Now, today I want to focus on explaining the algorithm at a high level, and I am going to give 0 Chernoff bounds in this talk. So rather than dig into the details of the probability calculations, I want to just stop and point out at points some of the underlying intuition about the probability and about the optimization that we do. This is joint work with Rafail Ostrovsky from UCLA. I want to begin just by defining compaction, tight compaction. So you have an array of objects that are blue and red. Here we use 3-digit numbers. And you compact, you push all the blue elements to the front of the array. Now, here we used half of the elements being blue and half of the elements being red. This does not need to happen in general. It sort of makes the examples easier, and it makes the runtime a little faster if you happen to know that all the elements are blue and red, or that half the elements are blue and half are red. But there's a quick reduction. Additionally, notice that the blue elements' relative ordering has changed from the first line to the second line. This means that the sort is not stable, or the compaction is not stable. For Oblivious type compaction, you have a client that has almost no local memory. They have big O of 1 words, where a word has size log n, which is, you need it to be at least log n to even store the address of something in an array of size n. The remote server has big O of n words, and the client has, in some previous step, stored their data on this encrypted server, and the server encrypted with their own private key. So the client has a sequence of memory accesses that are data independent, meaning either it could be defined in advance or it's randomly generated. Regardless, it has no dependence on what's actually on the server. So each time client sends some value I to the server responds with A at I. Client says some calculation and overwrites A of I with the new value. And at the end of this process, you should have, again, an encrypted list that has now been compacted so that all of the marked elements are at the front. If it's deterministic, this should be guaranteed. If it's a random sequence of accesses, then you have at least a high probability of success. So you can think about using this as either as an independent primitive. So for example, if you want to flag a certain subset of your cloud server to get deleted, then you compact that to one end and then delete. You can also use it as a building block in ORAM. So for example, the delete half your array thing is faster to run just as compaction rather than using ORAM, but in addition, you can use tight compaction in order to implement ORAM. And additionally, I'll remark that there are a number of applications here, from the tight compaction to questions in routing and networking. This may seem a little counterintuitive because the goal in a networking problem is to generally distribute packets among nodes as evenly as possible, which might seem like the opposite of trying to push all elements to one side of the array. But as we shall see, the two problems actually sort of complement each other, are connected to each other. Now, there's an n log n lower bound for this problem in the case where the compaction algorithm is stable, where, in other words, the relative ordering of blue elements and red elements are each preserved. But if you remove that lower bound, then you can do better. So it's first done, we got an n log n by Mitchell and Zimmerman, and then again by the same authors, Lin Shishi from above. And finally, this was pushed to big O of n, which is, of course, optimal in the important OptORAMa paper. That paper both gives a deterministic tight compaction algorithm and the first asymptotically optimal ORAM construction. So that's big O of log n overhead. Our research came from sort of wondering if we removed the requirement of deterministicness and use randomness, and then actually try to optimize constants, how fast can we do? And the answer here is that we have an algorithm that runs in time 23,913 n plus little o of n. The server is guaranteed to learn nothing from the tight compaction procedure, and the probability that the array is not tightly compacted at the end of this protocol is negligible. 23,913 n is still not exactly fast, but it is a marked improvement. I'll just sort of throw this table up here and sort of comment on a few of these things. We're going to discuss these sort of segments of the algorithm in more detail throughout the paper, or throughout the talk today. But I'll note that OptORAMa does not give a constant and is not trying to optimize constants. It's merely trying to prove asymptotically optimal bound. But if you look at the expander graph construction they have and use the Jimbo-Marawoka construction, which is optimal from what's known, then it would imply a runtime of at least 2 to the 111n, which is very large. I'm also going to comment here that the both our algorithm and OptORAMa use the same sort of, you could call it a trick here, which is that if you shuffle into small enough bins, then you can pack metadata about those bins into a single memory word. So this is sort of a hack to get around the big O of 1 client memory size. As a warm-up, I'm going to give a very easy algorithm that is very slow. And for now, just assume that half the elements are blue and half the elements are red. Choose randomly an element from the left and an element from the right. If they're out of place, you swap them, and then choose again. Now, if they're both the same color, or if you pick blue on the left and red on the right, you just do nothing. So you have the same list all over again. When the number of balls on the left that are red or that are blue on the right is high, it's very easy to find balls to swap. So it takes big O of 1 time, in fact. But as the density gets low, this takes much longer. In fact, even the last step alone takes, on average, n squared over 4 time. N over 2 steps, or 2 over n is the probability that you grab something right on the left and on the right. So you need to multiply this together and then invert to get the expected time. So just doing the random swaps alone is a bad algorithm, but it's a totally useful tool to reduce the density below some constant value. You can do this by doing the exact same algorithm before random swaps, or in OptORAMa, they instead use a bipartite expander graph and proceed through edges of that bipartite expander graph doing swaps. For information theoretic reasons, nothing is going to give you faster runtime than random selection without information about the distribution. But running this, if you want to push the density below rho, then the probability that you grab a red element on the left and a blue element on the right will be rho squared, and so that should be gamma in the bottom of the integral. So if you want to push the density below gamma, you do the integral of d rho over rho squared, and that gives you times n the run time to push the density. Now, this means if you need a very small density, then this is an expensive procedure. And so we introduced the following sort of trick of what I call airlocks. So from left to right, we have blue bluish purple, reddish purple, and red, where the blue is mostly blue with a very small density of red, and then purple, bluish purple, and reddish purple are much closer to like 50-50, and then the red is mostly red with some small density of blue. So by swapping between the bluish purple and the reddish purple, you can quickly control the density in that central area, and then you perform swaps on the left side and on the right side. So now if, for example, on the left side, the density of blue elements in the bluish purple area is kept above some constant alpha, then you have, again, an integral from gamma to 1 of d rho over alpha rho. So really the speed up here is that instead of needing to grab a rare element from the left and the right, you have a difficult grab on the left and an easy grab on the right. And in terms of time, you improve from 1 over rho to log rho. So this is sort of the starting gadget we use, is that we isolate some constant size fraction of our array that will be pretty dense in one color. Then we have a tool that loosely compacts those dense areas. Looks like this. And then once you loosely compact them, so this, for example, loosely compacting an area that is mostly blue and all red gives you a new array that has all of the same blue elements as before, and with some of the red elements gone. So this has messed up your density numbers a little bit. So you adjust the airlock boundaries, you perform the density reduction step again, and then you repeat the whole cycle. Now, there's a sort of problem here that I haven't addressed, which is that balls are disappearing from our array in the loose compaction step. What's actually happening here is that from the left, mostly blue array, we're extracting a new array that's a mix of red and dummy elements. On the right, we extract a new array that's a mix of entirely blue and dummy elements. Sorting out those blue elements from the dummy elements or those red elements from the dummy elements will require another separate compaction step. But the loose compaction step is what we're going to describe in more detail now. So this is where we break up the loose area we want to loosely compact into very small bins, or relatively small bins of size log n over log log n. If you compute the probability here, but most bins are going to be pretty blue. More precisely, you can say that most of these bins are going to have the density, the density of red elements close to the density above. You can bound it by some constant. For the bins that are too red, you just get rid of them. Put them into a runoff array and deal with them later. So now we have either blue or entirely dummy elements, or mostly blue or entirely dummy. Next, for each of those bins, we divide them up again into even smaller bins of constant size. Now, if at the level above we have some constant, even very low density, we cannot stop some of these little constant size bins from having a lot of red. That's inevitable. But what we do is we pad each of them with some dummy elements, and we throw them into a random deregular graph. Now, what we're using this random graph for, we'll get to in a second, but we'll note for now that the edge set of this graph we can pack into a single memory word. And in addition, what we can do is we can have a single memory word that holds some information about what to do with that random regular graph. We can attach a direction to each edge and store it in a single memory word. To explain what this bipartite or what this random regular graph does for us and what makes it tricky to do stuff with, I want to give the way that this is handled in the OptORAMa algorithm instead first. So they do the sort of a similar thing that ends with a series of constant size bins that will generally be blue, but will have some red or purple. And they give instead this bipartite expander graph. So their construction requires this bipartite graph to have very large degree because they exploit something called self-rooting superconcentrators that are this old construction from Pippinger that allows them to assign weights to all these edges. So roughly, you take each gray box that is pointing to few purple or red boxes and take red balls from all of those purple or red boxes. And then after that, you ignore all of those gray boxes and the boxes that are now satisfied on the top, and you repeat the procedure. And for a sufficiently large degree of the expander graph, for the graph is sufficient, then you can show that this procedure will terminate. Now, so again, because we've packed all of the information about where the red and purple boxes are into a single memory word, we can sort of have the client do this whole calculation locally about which edges need to be active, which edges need to move balls. Once you have all of the edge weights assigned, then you can iterate through each edge and move balls along it using actual communication with the server. So a few things that are undesirable about this approach is the massive degree and also the fact that you need to add a whole bunch of new dummy elements. So the question is, does this bipartite graph help us at all? Or this random regular graph help us at all with improving the efficiency? There's some problems. On the left-hand side, we know what we're doing. We're moving red balls from the top to the bottom. Here, arrows can go either way. How do we assign directions to the arrows? Also, on the left, every red box has gray boxes below it that it can send excess red balls to. On the right, with some finite probability, for any fixed k, you have a red node that is connected only to other red nodes at length k or less away. So you have clusters of sort of arbitrary size of red elements. So there is no obvious way to push a blue element all the way over to that red element. So how are we going to more evenly distribute things so that we can then shrink it? Also, what does doing all of this do to D? And the answer to how we deal with all of this is a technique called majority bootstrap percolation. So first, I want to sort of explain what the goal here is. The goal is that, so we only treat as blue a node that has no red balls initially. And then we want to assign directions to all arrows so that for every node that is not blue, either red or purple, more arrows are pointing out than in. And then along each arrow, we're going to send a red ball out and receive and return either a blue or gray ball. And what this means is that after this procedure, the blue nodes can have at most D red balls. The red or purple nodes, because they have more going out than going in, also can have at most red balls, at most D red balls. So this has compacted the outlier red elements by a factor of D over D plus 1. So this is the loose compaction we desired. And the other important thing to note here is that, again, we can assign these arrows based only on the information about which nodes are blue and which nodes are red, which can be packed into a single memory word. Then, once this is done, we can get this compaction by visiting the arrows in an arbitrary order and doing actual client-server communication. So some questions remain. How do we assign these arrows? And the answer here is you do something you do sort of the greedy thing. You scan through all of the nodes, and whenever you hit a node that is red or purple and the majority of its neighbors are blue, you send all of its arrows pointing to blue as outgoing, so that now it has more nodes arrows pointing away than in, and you check all of its neighbors again. So this algorithm is guaranteed to work and run in linear time if it terminates. When does it terminate? So we can give an answer in two cases. One is that if the density is super sparse, less than any constant, but not negligible. It's like e to the negative log n over log n or something. Then you get that this is going to work with high probability. Or if the density is below some fixed constant, that's good enough for a random regular graph of degree at least 13. Well, at least 13 odd or at least 16 even. So with that as having gone through that, we can now give the entire algorithm more or less on a single slide. So here is the airlock compression using loose compaction on the far left and far right sides, taking off the runoff and pushing down. For each bin, when we want to loose compact, we shuffle that into small bins. We shuffle those bins into even smaller bins, treat the small bins as vertices of a random regular graph, and apply majority bootstrap percolation. After this, we have some runoff arrays to deal with. We have arrays that are a mix of, for example, blue and dummy elements, and then we just run the same procedure again all the way through. Now, when you get a mix of dummy and dummy elements, that's just all dummies, so you can get rid of it. But we also have other runoff arrays, for example, the purple box on the left, and those arrays will be sparse, and we run the same procedure again, and then the density gets pushed down to negligible and n. And once you do that at a depth of about 3, sort of traveling from mix of red and blue to mix of blue and dummy, and also traveling down in terms of sparsity, you get an algorithm that terminates. So that's the algorithm at a high level, and I just want to give a few more quick comments before I close. First of all, the result that this majority bootstrap percolation reaches everything is a new result, though it is not a difficult proof coming from the expander mixing lemma. It's, I think, still interesting on its own merits. Again, I'll comment that 23,913n is much worse than, for example, a simple recursive algorithm that gives 1/2 n log n, except for very large n. So it is an improvement on the constant, but it is not close to actually being implementable to give something faster. And we pose the following open problem. Can we de-randomize the constructions here to give something that still improves on the runtime of OptORAMa without too much of a blow up in the runtime from this algorithm with the deterministic algorithm? And I will stop there. Thank you.